Hello college algebra student, this video is for rational function, chapter 5.6 part 2. We continue with characteristics of rational function. In the first video we say for rational function you have to make sure that the denominator is never 0. So what does it affect the features of the rational functions? We also look at 1 over x and 1 over x squared. We discover some common properties among them, which is common for all rational function. Now there are always exceptions, so these are the common one. So the first one we talked about was vertical asymptote. Is a line where the graph tends towards positive or negative infinity as input approaches a. So x equal to a is not defined. It's a vertical line that is outside of the graph, but around x equal to a, the function shoot up or down. And then there is a horizontal asymptote. Most of them has, some doesn't have. Okay, it is a vertical line. It's a horizontal line because it's horizontal. Y equal to b, where the graph approaches y equal to b when x approaches infinity or negative infinity. Meaning these y equal to b is the end behaviors. Now this is the major thing that rational function difference from polynomial functions. We know polynomial functions, the graph usually like go up or down at the end, right? End behavior. Or they would go both up like that. So this is polynomial. But for rational function, there are cases where they do that, but not most of them actually would have a horizontal line where they would fall flat. So when x is very big, they would just be flattened out. It would not go to infinity like shoot up or down. They would just be approaching this horizontal line y equal to b. So y equal to b is a horizontal line where at the end behavior. So you no longer are dealing with when x approaches infinity, y go to infinity. It would be approaching b. Okay. The third thing is for some rational function, again is for some, not all of them has, like 1 over x and 1 over x doesn't have these. There is some point where it is undefined and there's a hole in it. So if you graph it, it's kind of like, oh, this is a rational function, right? They have these branches that go up and down, but suddenly there is a hole here there's a break. The graph just not defined. If you want f of this number, is undefined, and we call this we have a name for it rather than a hole. It's actually just a hole. It's also called more mathematically called removable discontinuity. It's discontinuity because when you draw the graph, you don't continue anymore. You break and then you continue. It's removable because you can think of it as just a hole. So if you put some cement back, you can fill the hole. So it's called removable discontinuity. This terms will show up in calculus. So we just adopt this term. It's a single point where the graph is not defined, indicated by an open circle. Okay, so but again, they may have vertical, horizontal, or slant asymptote. We'll talk about what slant asymptote, but they may have removable discontinuity or hole. They do not 100% have. The function may also approach positive and negative infinity on the left, on the right side, but most of the common one that we see in this course would have them both approaching horizontal asymptote. Okay, so important features of it. So how do we find them? Okay, so how do we find? So to find these vertical asymptote, horizontal asymptote, and removable continuity, the first things you need to do is you need to factor both the numerator and the denominator. Factor that now. Don't cancel them. Okay, don't cancel them. So the usually we factor them, like for example, x after we factor, x minus 2 is in the top. That's one factor. And the bottom, I have x minus 2 and x plus 3. It's very tempting to just cancel them, but that's not the case. They are there. They for a reason. So what happened is, if you have a common factor, like x minus 2 is a common factor, then you solve this when x is equal to 2. it is still undefined because it shows up in a denominator, right? So it is not in a domain, but it is not a vertical asymptote. It will be a removable discontinuity. So a common factor, that means it is x equal to, it makes the denominator as well as the numerator 0. It is a removable discontinuity. Okay, the second thing is, so the first is to identify the removable discontinuity. That is the common one. The second one is the vertical asymptote. The vertical asymptote is a factor of the denominator, but not the numerator. So it would be, just pretend that you have canceled this. Only this is the vertical asymptote. Okay, so domain would include both of these, exclude both of these actually. The removable continuity would be x equal to, the vertical asymptote would be x plus 3. So you would say x plus 3 equal to 0. In this case, x equal to negative 3 is a vertical asymptote. So it's a factor of the denominator, but not the numerator. That means it's a factor that you cannot cancel. For removable discontinuity, it's a factor that can cancel. And so for example, we have x minus 2, over x minus 2, x plus 3. Then x plus 3 is a factor of the denominator, but you cannot cancel the top. So you would say x equal to minus 3. So just as if you are solving x plus 3 equal to 0, x equal to negative 3, as if you're doing your domain, right? So this is actually a vertical asymptote. It's being excluded in the domain, but it's also a vertical asymptote. This one is a x minus 2. That means x equal to 2 is the removable discontinuity. Example 2. I have a function x squared minus 4x plus 3, x squared minus 9. So I want to find vertical asymptote, removable discontinuity. So what would it be? I factor it. Okay, so the bottom is x minus 3, x plus 3. The top would be, how can I factor? So two number, negative 4, when they multiply, they are 3, so it will be 1 times 3, but when they add, they're negative, so it will be x minus 1, x minus 3. So you see that the one that is common is x minus 3, right? So we'll say the removable continuity point is x minus 3 equal to 0, x is equal to 3. So when x equal to 3 is at, there is a hole there. And then what about the vertical asymptote? Vertical asymptote is when it is 0 in the denominator. So x plus 3 equal to 0. That means x equal to negative 3. This is a vertical line. So if I can visualize is x equal to 3, there's a vertical line where the graph is does not have a number, and also in x equal to 3 there is a hole. I don't know what it is. I have to plug in after I cancel. Then there is a hole here. I think if we cancel this and you will plug in 3 minus 1 is 2, yeah, it's a positive number, so it's like here. So after you graph it, there will be a hole here. We'll talk about how to graph the whole thing, so one at a time. And then the third thing is horizontal asymptote. So it's about end behavior. Just imagine when x is really, really, really big, we know for polynomial, it's just the leading coefficient that dominated, right? So what happens if you were dividing them? So you would be comparing the leading terms of both polynomial. So basically, you are just looking at the leading terms. So if the leading terms of so this is x to the n, a sub n, and this is a sub m, x to the m, assuming that xm is the largest in the denominator and xn is the largest in the numerator. So just imagine if you plug in a really, really big number. If they are the same degree, then they will cancel, right? So if they're the same degree, then the result would be they will approach the leading coefficients ratio. So they will approach a horizontal asymptote of y equal to an over am. So y equal to the ratio of the leading coefficient if the degree is the same. If the degree of the top is smaller, say for example, this is x squared and this is x cubed, then no matter if you plug in a really big number, x cubed will be really much bigger, right? So this would be equal to 0. Y equal to 0 is the vertical asymptote. But if the degree of the top is greater than the degree of the denominator, there's no vertical asymptote. It would become either a slant asymptote or oblique asymptote, where it's just like whatever degree of polynomial it is. So we say if the degree of the numerator is greater than the denominator by 1, there is slant asymptote. Okay, so let's do some example to illustrate this. If I have 2x plus 1, x plus 5, find the vertical, horizontal, and removable continuity. So vertical asymptote is just looking at the bottom, right? So VA would be x minus 5 equal to 0. That means the line is x equal to 5. Vertically, there is a line there. What about horizontal? Horizontal, we need to compare the degrees. This is degree 1, this is degree 2. They have the same degree. So horizontal asymptote would be y equal to, what's the coefficient? 2 over 1. 2 over 1. We would say because it's same degree. If it is the same degree, we just look at the coefficient. So that means y equal to 2. Do we have any removable discontinuity that is common? No removable discontinuity. Okay, this one, let's factor. X plus 3, and the bottom is x minus 5. X plus 2. Why? Because we can factor it as negative 10, negative 3, 2, 5, but negative 5. So that's how we write it. Do they have any common denominator? Okay, so vertical asymptote. Do they have any common factor? No common factor. The whole thing is a vertical asymptote. We have 2. X equal to 5 and x equal to negative 2. That's 2 vertical line, vertical asymptote. What about horizontal asymptote? We have to compare the degree. This is degree 1, right? The numerator is degree 1, the denominator is degree 2. So this is smaller. So the only horizontal asymptote is y equal to 0. It's always y equal to 0, because this is, if you have 1 million over 1 million square, this is going to be equal to 0. 1 over a very big number is going to 0. Do I have any common factor that I can cancel? No. So no removable continuity. The third one, so again, we're concentrating on factoring first, x plus 2, but don't cancel. You just factor them and look at them. X, is it the same here? So we just do x minus 5, x plus 2, but notice the difference. X plus 2 is the common one. If I am to find a domain, this 2 will be excluded. I don't care about canceling, but when I need to find horizontal and vertical asymptote, I have to make sure that, for vertical, I'll pretend that I'm canceling. Okay, so just this one is. So x minus 5 is used only, so x equal to 5 is the vertical asymptote. Okay, and then what about horizontal? I have to look at degree. So again, this is degree 1 over degree 2. So this is smaller. Smaller means when you are in the end behavior, so y is equal to 0. What about removable continuity? Which one is the common factor? This is a common factor, so the common factor is going to cancel. So x plus 2 equal to 0 is the removable continuity. X is equal to negative 2. That means when x equal to negative 2, you plug into the one that after you cancel, you'll find a point that is the removable continuity. So I'm going to stop here, and I'll talk about slant asymptote in the next section, next video.